So today I'm going to talk about the embedding problem of infinitely divisible probability measures on groups. You all must have seen the abstract, which is on the website. And so I'll start with introduction to the embedding problem, then mention some early results, and then embedding on Lie groups, mainly Dani's contribution to this field with his collaborators, and then some techniques, and then some embedding on locally compact groups. And any thing I have missed or mistakes are all mine, okay? So let G be a locally compact Hausdorff topological group. You can define PG, the convolution semigroup of probability measures endowed with weak star topology on it. A measure mu in PG is said to be infinitely divisible if for every natural number n, mu has an nth convolution root in PG. What does it mean? So you have a operation of convolution of two measures and probability measures, two probability measures. If you convolve them, you get a probability measure. So if mu has an nth root means there is a measure lambda n, which if you convolve n times, you will get mu. So it's infinitely divisible if this happens for every n in n natural numbers. So for example, if you take Dirac measures on R as say delta x, then it has nth root like delta x by n, Dirac measure at x by n. S1 is divisible, so all Dirac measures are embeddable. And or you can take periodic field QP, which is also divisible. And you also have something called exponential measures, which I'll explain in a minute. So measure mu in PG is said to be embeddable if there exists a continuous real one parameter convolution semigroup mu T in PG such that mu1 is mu. So what does it mean? So you have a map from T to mu T from say R plus to PG. It's a continuous homomorphism and mu1 is mu. So example, Poisson measures, which are called exponential measures. So exponential T lambda, you define as delta E plus summation n from 1 to infinity, T to the power n, and factorial lambda to the power n. So that's the convolution power. And instead of delta E, you could also have a Haar measure at some compact group with some suitable. Lambda is a measure, any positive measure, and then you have to normalize this. That will make it a probability measure. So, and so delta is Dirac measure at identity E, but you can also have their omega H, where H is a compact subgroup and omega H is Haar measure, and then lambda should be commuting with that omega H. And Gaussian measures, Dirac measures. So more generally, on any connected nilpotent Lie groups, you can have Dirac measures supported on elements coming from one parameter sub. Because these are exponential, connected nilpotent group is exponential, so every element would lie on a one parameter sub. So note that every embeddable measure is infinitely divisible because you have mu, if you have mu equal to mu1, then it has nth root as mu or sub 1 by n. Because this is a semigroup, so it's power 1 by n. Mu1 by n to the power n is mu1, which is same as mu. So every embeddable measure is infinitely divisible. What we are interested in is conversely, is every infinitely divisible measure embeddable? Can you, given a measure with roots of all order n, can you find a continuous real one parameter semigroup of probability measures where you can put mu as mu1 or mu as any mu t, doesn't matter. So this was raised as a question by Parthasarathi in 1967. In fact, he proved embedding for measures which on a connected semi-simple Lie group with finite center where the measures which commute with the Haar measure of maximal compact subgroup. If they are infinitely divisible, then they would be embedded. He also proved around the same time that if you have before that in any infinitely divisible measure, though the year is same, so I don't know it's before or after, but any infinitely divisible measure on SL2C can be embedded in a dyadic semigroup. So this was raised as a question by Parthasarathi and then slowly came to be viewed as a conjecture when some evidence was gathered. And Dani has made major contributions toward resolution of the embedding problem, as you will see from the rest of the lecture. Yeah. No, it's not. You will see also. In some case, in R, it is unique, on R. And in some other cases, you will see. Why the embedding problem? So on Rn, any embeddable measure is a convolution of a Dirac measure, a Gaussian measure, and a Poisson measure. In general, the structure of continuous one-parameter convolution semigroup is well understood with, there is a Levi-Khinchin formula for the structure of one-parameter convolution semigroup, continuous one. And embeddable measures can be approximated by Poisson measures, and they also appear in many other fields, for example, in central limit theory as limit of commutative infinitesimal triangular system of measures. Like this is akin to law of large numbers on real life. Okay, so okay. So early on, the embedding problem was solved for the following. So on Rn, which is very old, by Levy, Paul Levy. In fact, every infinitely divisible measure on Rn has a unique nth root, and since the root set of a measure on Rn is relatively compact, you can find an embedding. So I will say a little more about how you do that. So compact Lie groups, again, the root set is a compact set. So you take, say, square root, then n, say, so every n factorial root you take, its nth power will be n minus 1 factorial root. And because each of these are compact, you can successively choose map from Q, which is a semigroup, Q plus, which will be a semigroup, and you get a semigroup embedding of Q plus going to P of Rn. And then there is a general theory that if you have such an embedding where image of 0, 1 intersection that's Q plus is relatively compact, then you can extend it to a real one parameter. So same thing about connected nilpotent Lie groups, that set of roots is relatively compact. So that was done by Burrell and McCrudden. Then, so McCrudden also showed that on a connected Lie group G, if the support of mu is large, that is the closed subgroup generated by the support of mu is whole of G, then mu, if mu is infinitely divisible, then it's embedded. So in 1985, Dani met McCrudden at Oberwolfach in a conference, which is part of a series, probability measures on groups. And they started working together and continued working by sending letters through post. All of you young people probably haven't heard of post, right? Certainly not working on post by letters, right? Communicating. So And yeah, the first email started in late 1990 or something like that, right? Or mid 1990. TIFR had one terminal for whole of TIFR in the Computer Science Center. And if you want to receive an email, then the person has to write in the subject line that it is for so and so. But it was accessible to everybody. So their first paper appeared in the proceeding of the same conference, where they proved the embedding for infinitely divisible measures on semi-simple groups with finite center, whose support is not contained in any parabolic subgroups of G. And there are lots of subgroups which are not parabolic subgroups or not containing parabolic. And this was just the beginning of the, whatever solving of embedding problem. Then we have the Dani effect on the embedding problem. So in a series of papers with Margulis, Dani solved the embedding problem for several class of Lie groups. And you can see the effect because what was done by Margulis before had many of them had quite different techniques from what is done now. And here Dani's expertise on structure of Lie groups and also probabilities on groups, and you can see many things, or study of orbits and so on, which would be reflected in this. Many of them are very deep techniques, especially the paper in 1992, where it showed they proved this, that any infinitely divisible measure is embeddable if G is a closed linear group, simply connected Lie group, connected semi-simple Lie groups. So main thing is they proved it for a group, which is a general group, which has a linear representation with discrete kernel. So if you have a group G and it has a representation to GLV, where V is a real finite dimensional vector space, and the kernel of this is discrete, then any infinitely divisible measure on it is embeddable. In fact, they later, in a later paper in 2007, they labeled this class of Lie groups as class C. So let's talk about some techniques. Some of it is general and some of it is by Dani and Margulis. So let R mu denote the set of convolution roots of the measure mu, and Fu mu denote the set of factors, two-sided factors of mu. Okay, so naturally R mu root set is contained in factor set of mu. And so, sorry, there is a typo here. It should be Q plus to PG, not Q to PG. So you can find a rational semi-group embedding from Q plus to PG with F1 to mu, which is locally tight, and F01 intersection Q is relatively compact. So if R mu is compact, then you're done, because such a embedding can be extended to real embedding in case of Lie groups. Not always, but in case of Lie groups. So, but how do you find that R mu is compact? In general, it's not true unless your group is compact or compactly generated nilpotent groups. So there is so you work on factor compactness first. So if it's not, I mean, it need not be factor compact also, because if it's factor compact, it's root compact. I mean, set of factors of mu need not be compact. If anyway set of roots of mu is not compact, then there is no hope for factor set. But you can find a shift of factors and you can put them in a compact set. So if you have lambda in a sequence in which is in the factor set of mu, then you can find a sequence xn such that lambda and xn and lambda and xn inverse are relatively compact. And when you have lambda and xn is relatively compact, the other part, say nu n, if lambda and nu n is mu, then other part is giving you delta xn. Inverse nu n is relatively compact. And if you just change the order, what you will get is the conjugation sequence xn mu xn inverse and xn inverse mu xn are relatively compact. Now you see this is a conjugating sequence of mu. And either you, so these are unbounded if your sequence lambda is n is unbounded, but they may be bounded modulo some group which may help you. Or you may choose your factor sequence to be roots, which are not all roots, but roots restricted to some subgroup. So if you want to show that F mu is compact, you need to show that Xn is relatively compact. That doesn't always happen, as we know. Life is not fair. It is not easy to solve things. So, and if it's easy, it becomes not so interesting. So for a linear, so this is one of the techniques of using these, because we have this conjugation action. You want to study conjugation action of G. So if G is a linear group, then you can, so G is subset GLV for some vector space V, which embeds into MV, which is the vector space of all linear transformation from V to V. And conjugation action of G extends to that of GLV and hence to MV, because it's just a conjugation action, right? So it can extend to larger space. So then there is a simple technique developed by Dani to study when a sequence of these maps, we are talking about conjugation maps, but sequence of any invertible linear maps on a vector space is relatively compact in terms of behavior of its orbits. So this in particular led to what is called convergence of type theorems by Dani, which is if you have a sequence mu n converging to mu and tau n mu n converging to nu, then tau n is relatively compact under certain condition. Example, if support mu and support nu, sorry, gamma, this is gamma, not, or it's nu, gamma. So support mu and support gamma are large on a connected Lie group, which has no compact central subgroup of positivity. So large, as I explained before, that a measure support mu is large if the group generated by support mu is dense in the whole group G. So in the above scenario, it will give you the following. So for example, you can also have Zariski density if you are in an algebraic group. So for a measure mu on an algebraic group, it follows that Xn can be chosen to be in Z mu, which is the centralizer of support of mu. Okay. And then if R mu is relatively compact, then R mu is relatively compact, it's either Z mu is compact, or if you say that G mu is Zariski dense in G, then Z mu will become the center of G. And there is a result by Margulis that if you have root compact measures, so measure whose all roots are compact in the projection modulo the center in a Lie group, then the original roots are also relatively compact. So you take a sequence in G and you go G modulo center. And in G modulo center, if you have these sequence of measures which are relatively compact, which are root of mu, then original roots are relatively compact. And then you get the embedding of mu. But in general, you don't have that G mu is Zariski dense in G for linear groups, or you don't have that Z mu is compact. So for a general infinitely divisible measure on an algebraic group, what do? So they try selecting roots of all order in a particular subgroup H, such that some more conditions will be satisfied. So Dani and Margulis find a subgroup H of G such that mu is infinitely divisible in PH, means the They are all supported on that group H. And there is a simply connected nilpotent subgroup N of Z mu, modulo which this sequence of roots will be relatively compact. So you have lambda and xn is relatively compact for some xn belongs to N. Okay. So now you have reduced your Z mu to this subgroup, simply connected nilpotent group N, but it is still not, lambda n's are not relatively compact. And this one is not central, so you can't do anything. Now, what do? You have a shift sequence, which is lambda and xn, which is compact, but lambda n's are still unbounded. So what do? They magically turn these lambda and xn into roots of mu. So how do they do that? So they show that there is Zn belongs to Z mu intersection n such that if I take conjugation of lambda n, Zn lambda and Zn inverse, it is actually lambda and xn. And these are roots of mu. So Zn lambda and Zn inverse to the power n will become Zn lambda and to the power m Zn equal to, now this is the mth root, so Zn mu Zn inverse, which is mu because Zn belongs to the centralizer of support. So this one is same as mu. So see the ingenuity of this, that you had an unbounded sequence, then you got shift to be bounded. Now shift you cannot embed that. So they turn it into roots and then, so now that root sequence Zn lambda and Zn inverse is bounded, right? So, and of course you have to do these simultaneously for all n factorial roots, not just nth root. And then you get an embedding of mu. So since one has relatively compact sequence of roots, which are conjugation of the original roots, one can find a rational and hence a real embedding. So Dani and Margulis showed that any homomorphism F from Q to PG is locally tight for a connected Lie group G. So it is enough to find such a rational homomorphism. Once you have an abstract homomorphism from, sorry, so again, this is Q plus. I have made a mistake here, Q plus. So if you have a rational semigroup, then it is locally tight. And then it would extend to real. But how do you find such a rational homomorphism? Rational embedding. So it is sufficient to choose a particular set of nth root which are contained in a compact set. For example, if we have a symmetric infinitely divisible measure with whose all roots are symmetric, then you can go to the convolution operator on BL on L2G, and you will get that that convolution operator has symmetric root which is unique. So since you have a root which is unique, sorry, I have gone forward. So root which is unique, where did I go? Oh, there's too much, okay. Then you have a rational embedding because all roots are unique, so you can define an embedding. And then by that theorem above, you can say that that is locally tight, and then the mu equal to mu1 will have embedding which is real. So for G in class C, which I mentioned, so what is that? There's a linear representation rho from G to GLNR with discrete kernel. And it's a discrete central subgroup, which is because it's discrete and normal, so it's central in the group. And one can also change the representation to get that the image is closed. See, originally the image may not be closed, but you can tweak the representation to get the image to be close. Your n will become larger. And this is in one of the papers about unipotent orbits of Dani with Margulis. Then one can choose the roots of mu in such a way that its images are roots of rho mu. Remember, the previous information was about linear groups or algebraic groups. And then these images are relatively compact. And since the kernel is a central subgroup, these roots of mu are also in a compact set by result by Margulis, and hence mu is embeddable. So here you can go modulo that discrete kernel, which is a central subgroup, and you can do this. Well, there is little more here which I'm not saying, but because it's not as simple as it looks. So note that any connected Lie group G, the quotient group G by T, where T is the central torus, maximal central torus, is in class C. So class C is characterized as that it's a connected Lie group G that if you take a solvable radical R, then closure of the commutator group RR does not have any central subgroup, means it's simply connected nilpotent group. So for any infinitely divisible measure mu in a connected Lie groups, you can choose a sequence Zn in G such that Zn T centralizes pi mu, means the image of mu in G by T for T being maximal torus, that you get Zn mu, Zn inverse converges to lambda, and lambda is embeddable. So what you have not embedded mu, but you have embedded the limit of a sequence of conjugation by some elements, and this is called weak embedding. Now, how does that help? The first thing it helps is that if I convolve mu with omega t, the Haar measure of the central torus, maximal central torus, then it becomes actually embeddable, because Zn mu star omega t Zn inverse becomes mu star omega t, and it's same as lambda star omega t, because Zn centralizes mu, image of mu in G by T. So for any infinitely divisible measure, if I convolve it with the Haar measure of maximal central torus, it will be embeddable. Okay, that still doesn't tell you that measure mu is embeddable. So for which class of Lie groups was the embedding problem not solved till 2007? Dani and Margulis have a paper in 2007 which gives simpler proof of their earlier paper and also gives this conjugating sequence and certain other things. So as you may have understood that whenever you have a non-trivial central torus, there is a problem. If it is not, then you can just embed it, right? Because it would work. So any generic infinitely divisible measure on a connected Lie group, unless it is in class C, you don't know whether it can be embedded. And if the closure of the commutative subgroup RR contains a non-trivial central torus. So sometimes you get an embedding for a specific measure because either if they are like symmetric with symmetric roots, or if they are large measures, you can get, right? Also okay, so now one is looking at a group which is solvable, and because if it's nilpotent, then there is embedding. So if it's solvable and it has a torus in its center, so that gives trouble. So compact extensions of, remember, if you have a torus but it's a linear group, you don't have trouble. So you want a non-linear group, and you also want a group which is not in class C then. So compact extensions of Heisenberg groups which have a non-trivial compact connected central subgroup T, and any linear representation has T in its kernel. So for example, you can take, okay, maybe I'll be anyway giving so the group of this type with the smallest dimension possible, for which the embedding problem was not solved then, is the so-called Walnut Group. And this term was coined by Margulis, I believe. He felt that it was a tough nut to crack, and but I think walnuts are easy, very easy. I love walnuts, and I don't think it's, but okay. It was, so these techniques were not working out for these groups. So this is the smallest. So the Walnut Group is defined as follows. Take three-dimensional Heisenberg group, right? So 1 A, B, C, 1, 3 by 3 upper triangle, strictly upper triangle. And then its center is the top right corner, which is isomorphic to R. So you go modulo discrete subgroup of that. And D of that, and take n equal to h by d. Now the center is a one-dimensional torus there, right? So, and there is a canonical action of SL2R on this Heisenberg group, which you may have seen, and it fixes elements of the center. So you can extend that action to n. And let K be the subgroup of group of rotations of SL2R, means SO2R, and take G equal to SL2R, semi-direct product N, and take W as SO2R semi-direct product N, which is containing G. This is your Walnut Group, okay? This W is called the Walnut Group. So it's a solvable group, right? It's and it is a four-dimensional solvable group because N has 3 dimensions, K SO2 has 1 dimension. It turns out that any linear representation of G or W will have T in its kernel. So it is certainly not. Neither G nor W belongs to class C because its NN is going to be T. So yeah, so WW will also have this T in it. So Dani with Guivarc'h, and so we got together and we started looking at it in 2007 when there was Dani's 60th birthday celebration in TIFR. And so this is one of the results which was shown that the embedding problem is solved for walnut groups. So this is the walnut is cracked. I hope I can eat some of it. So let G be a semi-direct product of SL2R with NS above, and any closed connected subgroup of G, if you have, then any infinitely divisible measure on M, that subgroup, is embeddable in PM. In particular, every infinitely divisible measure on the Walnut group is embeddable because I can take M as the Walnut group. And the above is proved with the help of the following general result, which is somewhat technical and has some conditions on the group and on the measure. So this I called a general theorem or main theorem. So if G is a linear group admitting a surjective continuous homomorphism from G to an algebraic, almost algebraic group G tilde, such that kernel is containing center of G and kernel of P has a compact connected component. So the kernel will look like some discrete group times the torus. And let Q from G to G by T be the natural map. And if let mu belongs to PG be such that this image has no idempotent factors, means Haar measure of some non-trivial compact group should not be, not just commuting with it, but say omega H star mu is not mu, and commuting also. So no idempotent factor. So only idempotents in PG are Haar measures of compact. So no non-trivial idempotent factor because delta E is always there. If mu is infinitely divisible, then mu is embeddable. And so first condition is satisfied if G is a compact extension of its commutator subgroup, or if you add G is a compact extension of commutator subgroups times the nil radical and closure of this. And this is satisfied if the solvable radical of G is a compact extension of nil radical. And the second condition is satisfied, for example, if the support of mu is contained in the nil radical of N, because N by T is a simply connected nilpotent group, so it has no non-trivial compact. So for example, Walnut Group, the first condition would be satisfied, but not, I mean, we are taking any measure mu, so only mu if it is supported on the nil radical, then second condition will be. So using this general theorem, following was shown. So any infinitely divisible measure mu on a connected Lie group is embeddable if the support of mu is contained in the nil radical of G, or if G mu by its commutator subgroup is compact. So these are specific cases. And for example, condition 2 is satisfied if G mu has property T, but there are many other examples which doesn't have to have property. The proof uses all the techniques developed by Dani with Mcrudden, some more developed by him for the general theorem and us, and some results derived from the work on concentration functions, and following resulting Fourier analysis, which was also proven for in this paper. Sorry. Okay, so this is, let K be a compact connected subgroup of GLDR. So it's a linear compact group, and such that the K action on RD has no non-zero fixed points. And if you take lambda to be a K invariant probability measure on RD, such that lambda V equal to 0 for any proper subspace V of RD, then lambda to the power D has density in RD. In particular, lambda hat vanishes at infinity. Fourier transform, because it's an RD. So far we have got the following for any infinitely divisible measure on a connected Lie group G. So the first one is that mu star omega T is embeddable, where T is the maximal central torus of G, or of RR, where R is the solvable radical. So there exists Zn in the centralizer of support of mu star omega T, such that Zn mu Zn inverse converges to lambda, and lambda is embedded. So a conjugating sequence of mu is has a limit which is embeddable, and mu star omega T is embeddable. So these two are general result, but you can take T to be trivial if your group, so RR has no compact central subgroup, RR bar is simply connected, then T is trivial, and those are the groups which have linear representation with discrete kernel. Okay, so that is the third one, saying that mu is embeddable if G is nilpotent, or G has a linear representation with discrete kernel. And mu is embeddable if G mu, the closed subgroup generated by support mu, satisfies one of the special properties mentioned above, right? That is, that support mu is large, or support mu is containing connected nilpotent normal subgroup, or G mu by G mu closure is compact. So now I will just list some easy consequences of our result. So we already say mu star omega t is embeddable, but we are using roots of mu to show the embedding. So because we took the image in G by T, and then we took some shifting sequence from centralizer of the image and so on. So you can conclude from this embedding that actually you can find a subgroup H on which mu is infinitely divisible. And this subgroup H is of course not that subgroup H, but new subgroup H, which is of this form, which is you take mu star omega t, take G of that, G mu star, and take normalizer of that group, G mu star omega t, and take its connected component. So that is actually normalizer of G mu t and its connected component and G mu. Okay. So mu is infinitely divisible on this. And if the G mu is discrete, then actually you can show that N0 mu omega t is actually Z0 mu omega t, and you get H of this form. If G mu is connected, then just H is N0 mu omega t, and actually G mu t is normal in that. So if G mu is nilpotent and connected, then G mu t is nilpotent and connected, and it's normal here. So it's contained in nil radical. So you can get these, what Dani would call piecemeal results. But I have put them just to give you some idea. So any infinitely divisible probability measure on a connected Lie group is embeddable if G mu is. So first one is G mu is contained in the center of G, because we have taken a conjugating sequence whose limit is embeddable. But if the support is in center, then conjugation gives you the same measure. So Zn mu, Zn inverse is just mu. And if it's converging to lambda, here you can see, oops, sorry. Oh, my goodness. It moves slow and then it moves too fast. So G mu is in the center of G, support of mu is in the center, then this is just mu. So lambda is mu and mu is embedded, right? Then if G mu is connected, then it's contained in this N0 mu omega t, and it's nilpotent, then it's contained in nil radical of this group, subgroup. So you don't need this to be in the original nil radical, but if it is just connected and nilpotent, you can get it to be in a subgroup where it falls in nil radical. So you can embed it. Then these are G mu n, where n is nil radical is dense in G, follows from some old result where it says that in such a case, mu is actually has all the roots in a compact set. Then if G mu is discrete, you get a form like this, and then you can prove that you can choose the conjugating sequences into the centralizer of support of mu. So it becomes again full of mu. And the last one is just a simple observation that if you take mu is infinitely divisible on G mu itself, so G mu need not be connected. When it's connected, then you say mu has large support and you can do it. But here also you can use the linear representation and work on algebraic group and go back and so on. So you can do that. So that is about, now there are some results by Dani which discuss embedding problem on a general locally compact. So one of them is with Claude-Schmidt. So mu is infinitely divisible on G such that support mu is contained in, say, some vector group, real vector group RD. Then it is infinitely divisible on RD itself, and then we know that it's embeddable. So, and this was another result where any infinitely divisible measure on a discrete finitely generated subgroup GLNA of GLNA is embeddable. So when you have a discrete group and if you have embedding, then it is always Poisson. So it looks like that exponential which I wrote earlier. And the proof uses results on real linear groups as Dani and Margulis had developed. And the following, which is that any measure on periodic algebraic group is infinitely divisible if and only if there exists a unipotent element X in the centralizer of support mu such that X mu equal to mu X is embeddable. And one of the techniques developed by Dani, for example, G subset GLV subset MV and conjugation action, you take it on a vector space and study, also is useful here in periodic case. So I would like to mention one result of Dani, which is kind of inherently used in convergence of type theorems and these things about vector space and so on. And this result has been very useful over the years for me in many of my work. And it was really useful in embedding directly or indirectly. So this is about study of automorphism groups of a connected Lie group. There's a result by D. Wigner that for any connected Lie group, G, the connected component of identity in the automorphism group or G is an almost algebraic subgroup of GLG. I never mentioned what is almost algebraic. Most of you know algebraic. Almost algebraic means it's a subgroup of finite index in an algebraic group. So algebraic group is rational points of algebra. So an algebraic subgroup of GLG where G is the Lie algebra of G. Now this does not hold for odd G in general, as odd of Tn, if you take a torus, is isomorphic to GL and Z, and if n is large, then this is a discrete infinite group. So only connected component will be trivial. So then for certain subclass of Lie groups, Dani proved the following result, which is very useful, as I mentioned earlier. Let G be a connected Lie group without any compact central subgroup of positive dimension. Then odd G is almost algebraic as a subgroup of GLG, where G is the Lie algebra, calligraphic G is the Lie algebra of G. In particular, odd G has finitely many connected components. So you can do many things like take odd G semi-direct product G and many, it's very useful, and you can also use things like convergence of type theorems and so on. And so I should also mention that Dani has used also his papers on orbits of ergodic quasi-invariant measures, and also his techniques are spread over many fields for solving these problems. So there is no clear distinction of this area or that area. And it's a pleasure to have worked with him, learned a lot from him. And the main thing I find very a learning experience is that with whatever he does, which is to me and to others, you must have seen in all these days that it's very vast, but he's a very, very humble person, and he's a very fine human being. And these are some of the references I may have missed. You can look at his MathSci.net paper, which page, which has more than 100 papers. And so there is a survey by François Ladrapierre with François Ladrapierre on Dani's work on probability measures on group, which mentions quite a few other things. There is also results with Raja and other people which are also there, you can see. And Yeah, so this is not exhaustive. I didn't change the references from that paper. Maybe I added one or two which I missed. Thank you, Dani, and everybody for listening. Happy birthday.
Questions or comments?
Well, Dani is right here to answer this.
Sure. Yeah. Would Dani want to make some comments?
Riddhi has been quite exhaustive, as I had not expected to the beyond the extent I had thought. So there's really nothing more I can contribute. Thank you.
Yeah, I'm sweating, but no, there are more things which I could have put, but I mean, there are some more on infinite divisibility and techniques which I have not added. So don't believe him. You want to learn, you have to go back to his work and learn. But I am hoping that he will solve the embedding problem. And if I have a tiny part in it, I'm okay with it. But so I have a tiny part in the Walnut Group thing. I mean, 3 of us did together. So I'm hoping that, but I like to do these little things every now and then, which he wants very profound techniques, new results, new ideas, because he has this experience and knows that with this you can go only this far and not beyond. So, and of course I believe him. So, but I like to fiddle with it. So I do these tiny things, some cases, which is not going to solve embedding problem, but in some sense, it always ends up with compact extensions of nilpotent groups and measure being. So actually, it's measure G mu and will be like co-compact in your group G. And that is a very difficult case, as I see. So, specific case like Walnut Group, there are some other things done, but yeah.
So if there are no questions or comments, let's thank Riddhi for a fascinating talk.